was that using ray diagram, describe the nature of the image formed when object is one placed at the principal focus and two placed between the principal focus and the optical center, the pole of the mirror. So because ray diagrams are drawn using straight edge, the reason for which I'm going to buy this. So you must also learn to use straight edge in drawing your ray diagram. So a very small aperture. If you want to cater for rays that goes beyond the aperture of the mirror, I say rule a vertical line behind it so that rays can cater for, or that will cater for rays that goes beyond the aperture of the mirror. And this is about concave mirror, so or converging mirror. And so we need to see the part that is coated and the part that is not. So the rule of the game is that R is equal to 2 times F. Very, very important. So if R is equal to 2 times F, then let me measure my focal length and also the radius of curvature. And I'm choosing 10 centimeter. So you know the radius of curvature, if my focal length is 10, R will be 20. So and this is very, very important. When you mix it, you've mixed up everything. So CF. A ray of light or the object is at the principal focus. F. Not a very giant object like Goliath, but something to represent an object. So if the object is placed at F, using ray diagram, let's draw. So a ray of light parallel to the principal axis after reflection. And here it's about you ensuring that whatever you are drawing as a ray is parallel. You are gauging. So when you have a ray of light parallel to the principal axis after reflection, the reflected ray must pass through the principal focus. One. So a ray incident reflection. Over here, there is limitation. The limitation is that you cannot use that rule which says that a ray of light passing through the optical, the principal focus after reflection must be parallel to the principal axis, in the sense that we are always drawing the ray coming from the head. The foot will always be on the principal axis. So you cannot draw a ray from the head to pass through F. Please, do you see it? Do we see it?
Yes, please.
We cannot draw a ray from the head to pass through F. So we are limited when it comes to application of that rule. But we can apply the other two rules. That a ray hitting the object or the screen at, the mirror at 90 must reflect along the same path. We can apply this rule. And when the ray hits it at 90, or we can also apply the rule that a ray hitting from the object hitting the pole after reflection must be symmetrical. This can also be used, but over here, the accuracy of it is by virtue of your accurate estimation that the angle must be equal to so if you do that so well, I think this works than this one because they are convergent. Okay, so we can eliminate it and then use two rules. So incident reflected. Incident reflected. Now, if all things are equal, what happens is that when we trace back the reflected rays, the two rays must be parallel. When we trace it back, the rays should never meet. Okay, so the rays should not meet in front, neither should they meet at the back. And if we are
Mr. Jia, please, the second ray is the one that's hitting it at 90 degrees. Oh.
This is one, a ray of light parallel to the principal axis after reflection must pass through the principal focus. And two, a ray of light hitting the mirror at 90 or perpendicularly after reflection must reflect and pass through a point on the principal axis, which is the center of curvature. Is that okay? All right. So, but the only challenge is that when you are drawing a ray coming from the object parallel to the, you have to try and ensure that it is parallel. If not, even what I've drawn, it is not exactly parallel. That is why the rays appears to be meeting over here. But when you gauge and draw it well, the reflected rays in front will be parallel, so will be the reflected rays at the back. And when you have a situation like that, okay, the inference we could draw is that the rays, the image is formed at infinity. Okay, the image is formed at infinity, which is magnified. Image is magnified. Magnified and real. Magnified and real. Okay, and inverted. Image is formed at infinity, magnified and real and inverted. One may ask, we said, yeah, how do you realize that the image is magnified? Image is real. The principle is that, you see, rays when the object is at the back between infinity and C, the nature of the image formed is that the image is real. All real images are inverted and it is diminished. So if you look at it, the image, the ray diagram we had when the image was behind C, we realized that image form is diminished, okay, inverted and real. When the object is at C, in between C, we realize that the image form is magnified. So as we move towards F, the image form is magnified and real. So by the time we get to F, yes, image will still be real and magnified. Okay, then the moment we move between F and C, it changes to be virtual, upright, and then virtual, upright, and then still magnified. So any position between C and F will have a magnified real image. It only changes when the object comes between F and C. That is the reason for which we could say that image is real magnified and all real images are inverted. Please, are we okay? Are we okay? Please, let me drop the attendance on the page. I'm not convinced, so much convinced with the number at the moment. All right, so any position in between the image in between C and F, exactly C and F, will have real, inverted, okay, and magnified. Any position between of the object between C and F, we have real, inverted, and magnified. Any position behind C, from between infinity and C, it is real, diminished. Okay. Now it changes when the object comes between F and C. Please, any question before we move on to the next? Okay, then let's look at when object is. Hello, Nanepia.
Please, you were establishing something. You were like, when it is between C and infinity, the image is real and diminished. And then you said something else. I didn't see.
What I was saying is that if the object is between infinity and C, you have an image that is diminished, real, and all real images are inverted. So the moment you are told the image is real, then it must be inverted. Or when you are told the image is inverted, then it is real. And so in between infinity up to C, you have real, diminished, the size is smaller than, okay, real, diminished, and then inverted. When it is the object is at C, we have same size as the same image size as the object. Then when it is between C and F, we have real, magnified, and then inverted. But the only change is that when it is at F, image is formed at infinity. So it will be real, magnified, inverted, but will be formed at infinity. And okay, are you okay?
The stadium, no. You said when it is formed at F, the image is formed at infinity.
When the object is at F, image is formed at infinity. So characteristics of the image formed will be image formed at infinity, real, and inverted. Then the image is also magnified. That is when the object is at F. Okay.
Yes, thank you.
Now, how we get this realization, because you see, lenses, the operation of lenses is similar to mirrors. Lenses are used in this astronomical instruments such as telescope in particular, and then microscopes. Telescope is for distance viewing. Objects that are viewed using telescope is at far distances. Okay, space, good. So the moon, the stars, okay, that are viewed using, and then the other heavenly bodies that are viewed using telescopes are at far distances. What happens is that whenever scientists are using this instrument to view the heavenly bodies, the stars, the moon, okay, at far distance, the image is always formed at Earth. And it is reversible. So when the object is at infinity, the image is formed at F. And when the object is placed at F, image will be at infinity. So it follows that reversibility principle of light, that when you place the object at F, the principal focus, the image will be formed at infinity. And so when the object is at infinity, image must be formed over here. So that is the basis on which we draw the conclusion that when object is at F, image must be at infinity and vice versa. Please, are we okay?
Yes.
All right.
Yes, please.
Now let's place the object between F and the pole to see what happens. Let me use a different ray diagram. So there's the aperture of the mirror. There's the center, which is the pole. Now, there's vertical line to cater for reflections beyond the aperture of the mirror. And it is so take your measurements, radius of curvature, and the focal length. So maybe I want to use 15 centimeter for F, and then 15 centimeter for 30 centimeter for R. So this is 15, And so it's obvious the end will be C. So this is E, this is F. This measurement is very, very important. Object is between the pole and F. So the instruction is that use ray diagram to describe the nature of the image formed. So my first, please, you are free to choose any of the rules. A ray of light parallel to the principal axis after reflection must pass through F. And I need at least two reflected rays to converge or appear to converge to form the image. A ray of light hitting the mirror normally reflects along the same path and then pass through a point on the principal axis. And this point is the center of curvature. So incident reflection. Okay. So I'm altering the rules. Now you could see that the reflected rays, okay, in front of the mirror as they travel, they are becoming more diverged. And so the chances of them meeting in front of the mirror is 0. So if you have a situation like this, extend the reflected rays backward. So I'm extending the reflected rays backward. At the point where they appear to converge, so the reflected rays appear to converge at the back of the mirror. Where they appear to converge will be the position for the image form. Now, when reflected rays appear to converge at a point, the image form is virtual because here the reflected rays do not actually meet, but they appear to meet behind the mirror. And once an image is formed which is behind the mirror, once an image is formed which is formed as a result of the apparent intersection of reflected rays, then the image form is virtual. So one characteristic of the image form. So one, image is virtual. Virtual because it is not formed on the screen or it is formed behind at the opposite side of the object. Virtual because it is formed as a result of the apparent intersection of reflected rays. 2. Yes, what is the second observation? What's the second observation? We have the image is magnified.
Image is upright.
All right. It's magnified. 3, it is upright. Upright or
Erect.
erect. And you can also add that it is formed behind the mirror. Formed behind the mirror. So these are the significant characteristics of the image forms. You see, so for concave mirror, okay, different kinds of images will be formed as a result of different object position. For different object positions, different images can be formed. But it could form a virtual image upon one position. That is, when the object is placed between the pole and the principal focus. That is the only situation where a concave mirror forms a virtual image. When object is between the pole P and then the principal focus. All other positions will be real. So let's quickly go through whatever we've seen. When the object is behind C or between infinity and C, image form is real, image form is diminished, image form is inverted. When it is real, it will also be inverted. An image is formed between C and F. Okay. When the object is at F, what happens? Yes, help me. When the object is at F, what will be the nature of the image form? Yes. Can somebody help? Yes, Amma. Oh, Amma, your line is fading.
Will be at
Okay, go ahead. Amma, go ahead. Okay, who else has a hand raised? Go ahead, Amma.
Please, the image formed will be at infinity.
When object is at C.
At C,
Yes.
the image form will be in between C and F.
No, Amma. Okay, Lizzie, take over. Lizzie, when the object is at C, what will be the nature of the image form?
Mr. Jefferson, when image is at F or C.
Object is at C.
Okay. The image is real. And the image is also inverted. And the image is it has the same size as the object. And the image is formed between.
No.
It's formed at C.
Formed at C. Yes.
Yes.
So when object is at C, image will be formed at C, image will be real, image will be inverted. It has the same size as the object. Now, Chris, are you there? Inshira, the two insurance, Ebresi, are you there? When object is between C and F, what happens? When object is between C and F, what will be the nature of the image form?
So please, the image be magnified.
Image is magnified. Image is magnified. Everybody go ahead.
I said the image is magnified.
But we are looking at the various characteristics. So I expect more from you.
Okay, I think the image will be upright.
No. Between C and F, one, image is real. All real images are inverted. So it will be inverted. It will be magnified, as you said. okay, and will be formed behind C, between infinity and C. Between magnified, okay, real, inverted, and then will be formed between C and infinity. Then when object is at F, image is formed at infinity, real, magnified, and inverted. When object is at F, image is real, inverted, magnified, and formed at infinity. Then finally, please, are you noting the characteristics of the various positions?
So you said for the between the C and F, the image is formed at C.
That between C and F, image is real, image is inverted, image is magnified, and formed between C and infinity, or behind C. Okay, when you place the object here, image will be formed behind C, meaning it is between infinity and C. All right. Then finally, when object is between F and the pole, that is the only situation where we have a concave mirror forming a real, a virtual image. Image will be virtual. All virtual images are upright or erect. Take note. All virtual images are upright or erect. So it will be virtual, it will be erect, it will be magnified, and it is formed behind the mirror. So we've gone through all the possible positions of the object in front of a concave mirror. Let's look at a convex mirror. What will be the general characteristics of images formed by a convex mirror? Please, do you have any question? Lizzie?
Please, it's not a question. I was trying to answer.
Okay, all right. Can you say something before we go to the drawing?
Okay. I was going to say that the image is virtual
Mm-hmm.
and is upright and
Mm-hmm.
also diminished.
Okay, let's see. That's what Lizzie said. Let's see if that is true. Epi, are you there, Yaba?
Yes, please.
Lynette? Okay, so for convex mirror, so for convex mirror, we have the reflecting surface curves inwardly. Sorry, outwardly. This is the pole. Then the principal axis. We take the same measurement. Same measurement as we measured for. So F and R. I'm taking 10 for F and so 20 for R. This measurement very, very, very important. F is virtual. So is C. Let me extend the principal axis in front. Object is always placed in front of the mirror. So this is my object. So the rules. A ray of light parallel to the principal axis. This one diverges rays. It's convex or divergent mirror. So ray incidenting on the mirror will be diverted. But the diverted ray always appears to be diverted from a point on the principal axis. And this point is the principal focus. So we must trace the diverted ray to the principal axis. Though it diverges ray, but the diverted ray always appears to be diverted from a point behind the mirror, and that point is the principal focus. A ray hitting the mirror at 90, okay, appears to be, will reflect along the same path and appear to pass through a point on the principal axis. This point is the center of curvature. You can also use a ray of light hitting the pole. A ray of light hitting the pole. Reflect at the same axis. And here you must measure your axis so well. If this is it, this must be the same angle. Then when you extend back the reflected rays, they will all converge, appear to converge at a common point. So here, in fact, I have used three rules, but we need only two. We don't need three. I'm using that to explain something to you. So this is the point where all the reflected rays appear to be converging. And that point would be the position of the image. Now, let's discuss the characteristics of this image. What will you say about the image as compared to the object? One, yes. Yes. Yeah, but what will you say? Give me one. Okay, Lizzie.
The image is diminished.
So image is diminished. Image is diminished. Two. Lizzie, go ahead.
The image is upright.
So diminished, upright, or erect. If the image is upright, then it also means that the image is what?
Virtual.
Virtual. What again?
Mr. Dear.
Erasing.
And please, this one is for images. There is a ray diagram of images placed surfaces formed on the concave mirror.
This is images formed, okay, in a convex mirror. Convex.
Okay, thank you very much.
We've done that for concave. So we are doing it for convex. And image form is between P and F. Image formed is between the pole and F. We are going to vary the position of the object to a different position. Draw a ray diagram to see what will happen. Okay.
Stay there.
Mr. Who is here?
Stay there, please. Yes, please. Please, I want you to show me the direction of the rays that I can see. The one you just did.
This is I applied one, a ray parallel to the principal axis after reflection must appear to, it will be diverted, but the diverted ray appears to pass through a point on the principal axis, and this is F. Then 2, I also use the rule that a ray of light hitting the mirror perpendicularly reflects along the same path and then passes through a point on the principal axis, and that is C. So this is the second rule. Then I was trying to clarify better by applying another rule which says that a ray hitting the pole reflects at the same axis. But we need two rules to form an image. But I was taking you through other possible rules, how you can apply the other possible rules. The reason for my drawing 3. Okay.
Yes, please. Thank you.
So let's change the position. Let's change the position of the object and draw a ray diagram to draw a conclusion for convex mirror. So take your measurements. The measurement very, very, very important. So F and R. If you are not given, the choice is yours. Maybe 10 centimeter or whatever you want to use. So I'm using 10. And so R must be 20. This is F. And this is C. Earlier, my object was close to the mirror. I want to take the objects a bit far from the mirror. So let's use the rays or the rules. A ray of light going parallel to the principal axis after reflection must appear to be diverted from a point behind the mirror. And that point where the diverted ray appears to be diverted from is the principal focus. So now this, I'm using a broken line to represent this because the image is a virtual one. Or this, what happens behind the mirror is always virtual. The reason for me using broken lines to represent anything behind the mirror, right? Now, a ray of light hitting the pole. The rays are always from the object. Hitting the pole reflects at the same axis. And that's the angle. So you must measure the same angle. You must measure the same, almost the same angle. Then, because this is one reflection, this is another reflection. There is no way these two reflected rays would ever meet to give you a real image. Because as they move, they are getting more diverged. Okay, the reason for us tracing the reflected rays backward and where they appear to meet will be the position for the image. If the reflected rays could meet in front, then a real image would be formed. But because they can never meet, okay, that's the reason for retracing it backward. And this is the point where the rays appear to meet. So this is the object, this is the image. Now let's discuss it. Image form is virtual, and so it will be upright. Image form is diminished, and image form is also between P and F. So in the first instance, when the object was closer to the mirror, we got the same characteristics. In the second situation, when the object is taken a bit far from the mirror, we are getting the same characteristics. If you extend the positioning from the mirror, you get the same thing. Okay, so we draw a general outlook that for convex mirror or divergent mirrors, image is always virtual. All virtual images are also upright. Image is always diminished. So virtual, upright, diminished, and always close to the mirror. That is why in divergent mirrors, we are told that, or it is written on divergent mirrors that objects you see in the mirror are always closer than they actually are. That is why we have that inscription written on mirrors that are used as side view and then head view mirror, because the image form is always closer to the mirror. And so images or objects you see in the mirror are always closer to the mirror than they actually are. They are real objects. Please, are we okay?
Yes.
Yes, please.
So that's it. If you have any question, ask. If you have any question,
Okay.
ask.
Mr. Ejia.
Priscilla,
Yes. Mr. Ejia, please, why didn't you draw the other? I can't see the screen.
come again.
Why didn't you draw the other line, like the one that passed through the sea?
The one that passes through the.
No. The one from the objects to sea.
Oh, I didn't do that because, Priscilla, I need only two. Okay, I just need only two of the rules to give me an image. In those instances where I gave you three, I was giving you how possible ways of doing this, the same thing. Okay,
Okay.
but you need at least two to give you an image. Amma,
So if a question is asked that why are diverging mirrors used as driving mirrors, it's because it enables drivers to see people behind them when they are in danger.
so that it has a wider field of view or range of view. Okay,
Okay.
than all other mirrors. And you see, the point that the image form is always closer to the mirror than they really are. It's an advantage when drivers are moving, are reversing, during reverse driving. Okay, if you want to go back, you are looking through the mirror. What you see in the mirror is always closer than they really are. And so at the point where you think you are so close to hitting the whatever you see or the image, you stop. Meanwhile, in the actual world, that is not the situation. So this becomes an advantage during reverse driving. Are you okay?
Yes.
So you may think you are close to killing whatever you see. Meanwhile, in actual fact, you are not close. Okay, but because you think you are so close, you quickly apply brakes in order to avert the danger. But in the real world, that is not what is happening.
Yes, please. Thank you.
All right. Please, any other question? So for convex mirror, we always have the same thing, the same characteristics, no matter where you place the objects. Okay, give me a minute to go for commercial break. I'll be with you. Just a minute, commercial break. Now there's another way we can describe the nature of the image form, but this time around using a formula. Okay, using a formula. Okay, and this is the mirror formula or the mirror equation. So what is the mirror formula or equation? We define the mirror formula or equation as a mathematical expression that relates the object distance, image distance, and then the focal length of the mirror. So the mirror formula / equation this is a mathematical expression or relation that connects the object's distance, we most often represent the object distance by the letter U. Connect the object distance U, image distance V, and the focal length of the mirror F. Please, these are letters. These are
Mr. Elia.
letters. Hello, Amma.
Please, sorry for disturbing, but I want to ask a question about the convex mirror again.
Well,
Please,
do
a
so.
certain book says the disadvantage. A certain book says the disadvantage of using convex mirror is that it creates an illusion that objects are further away than they actually are. So, what the book is
No,
saying, even to the opposite of what you are saying.
rather closer, closer. Rather
How is that a
closer.
disadvantage?
And that's why I said, you see, they will say it's a disadvantage, but that's why I said that it's an advantage when it comes to reverse driving. Okay, when it comes to reverse driving. And that one may also say that the fact that always objects or the images always look diminished is also a disadvantage. So the object is the image formed by a convex mirror always looks smaller than they actually are. So it depends on whoever is writing the book and creating a disadvantage or whatever. But it creates an illusion. It creates an illusion that objects are closer to the mirror than they actually are.
Okay, sir. Thank you.
All right. So this is a mathematical expression that connects or relates the object distance U, image distance V, and the focal length F. Okay, let me put it rather here. And the focal length F of the mirror. Of the mirror. Please, other books will use different letters. What is important is that you must define your letters. Where object distance is this. Okay, you must define your letters. Q is for this, P is for that, blah, blah, blah. But in most of the books, we use U, V, and F for these things, all right? Now let's see how the object distance, the mirror formula is derived. And the mirror formula applies to all kinds of mirrors, all kinds of spherical mirrors, all kinds of spherical mirrors. But I'm deriving it using concrete. So assuming this is my focal length F, I take the same measurement for C. Here you can place the object anywhere to derive the mirror formula. My object is at the center of curvature C. So using ray diagrams, I want to get the position of the image. Obviously, the image will be formed at where?
C.
C. But as for the C, I think you have all seen. So a ray of light parallel to the principal axis will reflect and pass through F. A ray of light passing through F would have to reflect and then be parallel to the principal axis. I suppose my ray is parallel. I hope so. So this is my image. Very, very close. Now, this is a point C. I'm labeling this point, a point A. This is F. B. This is D. O. And then a point E. Now I'm going to identify similar triangles. So I'm going to identify similar triangles. Triangles are similar when one is just a scale factor of the other. Triangles are also similar when they have the same interior angles. Triangles are similar when the ratio of their sides are equal. So I've given you 3 ways of identifying similar triangles. Triangles are similar when one is a scaled factor of the other. Two, triangles are similar when they have the same interior angles. When they have same interior angles. And 3, triangles are similar when the ratio of their sides are equal. This is how to identify similar triangles. Hey, Akosia Doma, Charlotte, are you there?
Yes, please.
Okay. So, if we look at, hello, Ama.
Please, I can't really see the board. It's like a light is shining on the board somewhere.
Oh, Ama, please, is it a general problem?
So it's better now. No,
Emma.
because I come again.
Let me see if I can make any adjustment because I'm not on any light. Is it better?
Yes, please.
Ama, maybe what you are seeing is an illusion, as you said earlier.
Second now.
Okay, so let me on the lights to see if is this better or worse.
It's better.
Better.
Okay, so if we look at triangle ACF and triangle FDO. Okay, please this side isn't curved. It appears it's as if we are taking this side as a straight line. Okay. If we look at these two triangles, we can identify something. That this angle is equal to this angle, vertically opposite angles. This angle is 90, and this angle is also 90. Then this angle will certainly correspond to this one. And so they are similar triangles. Okay. Because we have just identified that they have same interior angles. And so if they are similar triangles, then a ratio of their sides, the opposite side of this triangle, the opposite side of this one too, the ratio must be equal. If we take this side divided by this side, it must be equal, because the last condition, when triangles are equal, the ratio of their sides are also equal. So when I take the side of this triangle AC over DO, it must be equal to, when I take the ratio of this side, CF over the same side of the other counterpart, FD. It must be the same. When I take, and this must also be equal to AF over the same side of the other similar triangle, FO. I'm using the first features that when triangles are equal, the ratio of their sides are equal. Please, are we there?
Yes.
All right. So now, please open your eyes. So this is the object. It means that this is the object height, HO. This is the image. This side is the same as this side, because we are looking at these two lines parallel. So CE, which is the image side, is the same as DO. So AC, which is H subscript O, over DO, which is actually CE. CE is the image height, HI. This must be equal to CF. CF, what is CF? Please open your eyes. So we are looking for CF. But what is this distance? DF. What is DF? Plus, what is DF?
Focal length.
So F, the focal length. Then what is AB?
Object distance.
Object distance. So this is U. So if we have AB is the same as CD. AB is the same as CD. So if we are looking for CF, what will it be? I take it again. CD is equal to AB. AB is equal to U. Then FD is F. So what will be CF?
U minus F.
Exactly. So this will be U minus F, all divided by FD, which is F, equation 1. As for this ratio, we are not interested in AF over FO. We are not interested. Because either this is equal to this or the other way around. We have the two. So bye-bye. We are not interested in this one. So the ratio AC over DO is equal to CF over FD is giving us equation 1. And this is as a result of considering this similar triangle ACF and triangle FDO. Let's identify another similar triangle. So identify, let me claim whatever we have on top and then let's identify another similar triangle. Can somebody help me? We are identifying another similar triangle.
From the same diagram.
Pardon?
Please, is it from the same diagram?
Yes, from the same diagram. Earlier, we identified this and this as similar triangle. Can we identify another similar triangle? Or you want me to carry on? Okay, so when we considering triangle, you see, this triangle and this one are also similar triangle. Triangle CEF. Triangle CEF and triangle FBD. FBD are also similar triangles. We mean this one and this one. And when triangles are similar, they have the same interior angle. So this one is equal to this. This is 90. So is this side. And this side would also correspond with this one. Please, are we there? Are we there?
Yes.
So when triangles are similar, they have the same interior angles. Then the ratio of their corresponding sides must also be equal. So when I take CE over BD, so CE over BD, it must be equal to CF over LD, which must also be equal to this side, but we are not interested. We need only 2. Okay, so we'll only work with this one. Now, what is CE? What is CE? CE is the image height. H subscript I over, what is BD? BD is the same as AC, so object height. H naught. This must be equal to CF. CF. Now, this relates, please, let's look here, pay attention. Over here, we know from D, O to E, is the image distance V. So this time around, we will relate CF to V, not U. Even though they are the same position, we agree, but we are deriving a formula. So this time around, we use V instead of U as we applied earlier. So in that case, CF will be equal to V minus F. Please, are you with me?
Yes.
Yes.
So V minus F over FV, which is still F. We have equation 2. We are almost there. Please, if you are writing, quickly do so, so I can adjust the screen. Inshra, are you there?
Yes, please.
I'm just giving the notification that you've left the page, the physics page. So check and then restore yourself. So, Amma,
Mr. Asia.
Amma,
Mr. Asia.
yes, go ahead. Your hand is up.
Mr. Asia, please, I want to understand why you use V for the downside. Is it because no, why? Why did you use V for the downside and U for the
Well,
top?
earlier, you see, over here, it is because the image is at the same position as the object. Okay, we are free to use either U or V. Because from CD is U. The same CD is also V. So in our first situation, we use U. In the second situation, we are using V for CF. So
You can interchange them.
yes, it will get you to the same destination. So we have two equations. Please pay attention. We have equation 1, which is H naught over HI is equal to U minus F over F as equation 1. Hey, can you see? Can you repeat this? Please give me feedback. Can you read it?
No,
Okay.
please.
I think you can read now.
Yes, please.
Then equation 2, which is HI on H naught is equal to V minus F over F. Okay. Now,
Mr. Adia,
hello.
please, it's not me, because I'm still in the group.
Really?
Yeah.
Then I saved the name wrongly. I'll check.
Okay.
Now, this is HO. This is HI. I want to change equation 2 so that I have HO on top, HI down, HO divided by HI to look like equation 1. So when I do that, equation 2 will look like F on V minus F. Please, so equation 2 would actually look like this. Are we okay?
Yes, please.
And I'm doing this so that I can equate equation 1 and equation 2. If I do that, then class, I can equate equation 1 to equation 2. So I have U minus F over F is equal to F over V minus F. I have equated equation 1 and equation 2. When I finish, we'll quickly go through it again. So when we cross multiply, we have u minus f times v minus f is equal to f squared. I hope we are fine.
Yes, please.
When you open the brackets, we have uv minus uf minus vf plus f squared is equal to f squared. Over here, we are using math. So clearly, f squared will cancel out when we send it to the other side. Okay, so we have uv, let's send all other negatives to the other side of the equation. uf positive plus vf positive. Now the last stage is that I want us to divide through by UVF. So when you divide each of the sides of the equation by UVF, it is as if you haven't done anything to the equation. So UV all divided by UVF is equal to UF divided by UVF plus VF divided by UVF. And when we divide through by UVF, we have the last stage. We have 1 over F is equal to 1 over V plus 1 over U. Ladies, this is the mirror equation or formula. This is the mirror formula. So the mirror formula or equation is simply 1 over F is equal to 1 over U of V plus the other. You know, addition is commutative. So it can be 1 on V plus 1 on U, or can also be 1 on U plus 1 on V. This is so a mathematical equation or relation that connects the object distance U, image distance V, and focal length F of the mirror. And it applies to all manner of mirrors, whether convex or concave. And it also applies to all positions of the objects. Are you okay with it, or we have to go through it for the last time? Are we fine with deriving the mirror formula?
Yes.
Priscilla,
Yeah.
what did you say?
I don't know what.
I don't get you.
It's like split. I don't know.
So do I go through it once more?
Yes, please.
Okay. So I'm cleaning everything. I want us to quickly go through it again. Next time I will change the object's position. I said it applies to, you can derive that using all other positions of the object. So I'll change the object position from C. Adua Otubi, are you there? Ekuya,
Yes, sir.
and it applies to all kinds of mirrors. When we go through how to derive, then we see how to apply it to solving problems. So P is here. Let me assume F is here. I take the same measurement. So C is also here. Now, when I place the object behind C, or between infinity and C, I must get a diminished image formed in between C and F. So the rules, a ray of light parallel to the principal axis after reflection passes through F. Then a ray of light passing through F after reflection would have to be parallel to the principal axis. So the two reflected rays are meeting over here. And so that will be the image formed. An image formed is real, inverted, okay, real, inverted, diminished, and formed between C and F. All right. Now, O, A, this is B, D, this is already F. So F, E, so see if it's here, E, this is P, and lastly, this is G. So we identify similar triangles. We identify similar triangles. And when triangles are similar, one is they are a skilled R factor of the other. So triangle OAF is similar to triangle EPF. And when triangles are similar, they have the same interior angle. This is equal to this. This is 90. This is also 90. Please, this side is as if it's a straight line. Okay. And then this angle also actually alternates with this. And so they are similar triangles. When triangles are similar, the ratio of their sides, corresponding sides, must be equal. So the side OA divided by the side PE must be equal to the side OF over the side FP. Priscilla, are you there? Are you okay?
Yes, please.
So this is the object H naught. This is also the image height HI. So OA is H naught over PE is the same as BD, which is HI. And this is equal to OF. OF, this is U. From FP is F. And so OF will be equal to U minus F. U minus F. Over FP itself is F. We have equation 1. Let's identify another similar triangle. So considering triangle, this time I'll consider DBF. DBF and triangle FJP. This is a scaled up, okay, version of this. And these interior angles are equal. This is 90, this is also 90. And so this angle must correspond with this. The alternate with that. And so the ratio of their sides, BD over JP must be equal to BF over FP. Now what is BD? BD is image height over GP. GP is this. So that is H naught. This is equal to BF. BF, please look at something here. This is image distance V. That is DE. So if this is V, DE is V, and FP is F, then what will be BF? Chrysler, what will be BF?
Please, can you bring the camera up?
We have DE, which is the same as BP. This is V, BP is V, and FP is F. What will be BF?
V minus F.
Exactly. So this is V minus F over FP is F. So we have equation 2. We have equation 2. Let me underline to see if. So if that is the case, let's equate equation 1 to equation 2. Equation 1 is h naught over hi, which is equal to u minus f over f. And then equation 2 is this. We want to modify equation 1 to look like equation 2. So we invert it. hi on h2, which will be equal to f over u minus f. We equate equation 1 to equation 2. And so we have v minus f over f equal to f over u minus f. When we cross multiply, v minus f times u minus f is equal to f squared. So that when we open the bracket, we have uv minus vf minus uf plus f squared equal to f squared. This can easily reduce to 0. And so making the rest positives, you have vf plus uf. Because we want to create a general equation, we divide both sides of the equation by UVF. So if you divide through by UVF, you have UV all on UVF is equal to VF divided by UVF plus UF divided by UVF. So you have 1 on F equal 1 on U plus 1 on V as the mirror formula or equation, where F is equal to the focal length of the mirror, U is equal to the object distance, V is equal to the image distance. So no matter where you place the objects, you can derive the mirror equation or formula.
So dear, please, can you adjust the camera downwards a bit?
I hope it's better.
Yes.
Crystal, are you okay?
Yes, please.
Yeah, but are you okay?
Yes, please.
Please, this thing, the mastery of this is that you must spend time to go through it. Spend time to derive it yourself. Okay? You can easily master it or derive it when you've gone through it. Okay? When you are reviewing it along the line, if you get lost, then you refer to whatever we did and that's it. It's not difficult. Can I clean the board and continue?
Yes,
Yes, please.
Okay. We can also modify the same equation in diverse ways. One modification is this. You see, radius of curvature is equal to 2 times f. So you can also substitute. Hey, can you see?
No, please.
yes.
Some positions require that. Some positions require that. Anyway, we'll close soon. So or let me write on the line and write here instead. R is equal to 2F. So when we make F the subject in this relation, we have R on 2. Then when we substitute this into the equation, we will have 2 over R, because the inverse of this will be 2 on R. So this is one possible modification. This is still the mirror formula or equation. Another modification we can possibly have is this. Let's talk about magnification of the image. In fact, when we talk about generally, when we talk about magnification, we are looking at whether the image form is enlarged or diminished. So before our discussion, we were using magnification only for when the image is large compared to the object. But technically, when we talk about magnification, we are looking at whether the image is reduced or increased, either in size or in height. Okay, so technically, when we talk about magnification, we are looking at the size of the image compared to the size of the object. The object, when it is reduced, when its size is reduced, we say it's diminished. When its size is increased, we are saying it is magnified. But magnification refers to both situations. Now, we have two different kinds of magnification. We have what we call lateral magnification and we also have transverse magnification. When we talk about lateral magnification talks about laterally is side to side. When we talk about lateral, we mean side to side. So an object is in front of a mirror, whether concave or convex. This is the object. And this is the object distance, U. If the image is real, it will be inverted. Assuming the image is here, it means from the pole to the image position, this is the image distance, V. Now, when we talk about lateral magnification, okay, lateral is about side to side. So lateral magnification here, we are looking at a ratio of the image distance V to the object distance U. So lateral magnification is actually V over U. Then we can talk about the transverse magnification, a transverse sides. Transverse magnification is about its longitudinal end, where we are looking at image height ratio of the image height to object height. Hello, are you there?
Yes, please.
So this ratio is equal to HI over H naught. Now, experiment and theory prove that lateral magnification is always equal to transverse magnification. And so V on U is always equal to HI on HO. And this is equal to anything magnification, M, small letter m. So whenever you are looking for linear magnification, we call it linear magnification because we have angular magnification as well. Whenever you are looking for linear magnification, M is equal to either V on U, which is also equal to HI on HO. I'm sure you have seen this equation before. I think in pinhole camera. Okay. So the mirror formula can also be modified. M is either this or M is either equal to this. If we are only interested in V on U, then we can modify this and put it in. Unless we have a few minutes to end. So let's end at that. If I want to modify this equation to suit M, now what I'll do is that from the equation, I'll multiply through by M. From the mirror formula, I'll multiply through by M. So multiply. Oh, my lesson is off. All right. My earpiece is off. So class, let's end here. Okay. We'll continue on Friday. Please, is that okay?
Yes.
Hello, can you hear me?
Yes, please. Yes, please.
All right. So this is where I draw the curtains on today's meeting. Thanks for your time and everything. We'll have another wonderful session on Friday. If you have any problem, please do not hesitate to WhatsApp me, and I can even call you to give you explanation. Until Friday, please take care of yourself. And bye-bye. Please, the assignment I gave you on the platform, I want feedback, okay, by today ending. Okay?
Miss Dadia.
All right. Bye-bye.
Miss Dadia.